All right, are you done? Because this is about the amount of time you'll have for this type of question. What? Just three values, just random, you know, alpha 0, alpha 1, alpha 2, beta 0, beta 1, okay? Do it. So one thing I want to get to with this, one of the two things that I'll use this for is first to motivate. So if you take, so what's the length of this? The first one has length 3, right? The second one has length 2. What is the length of the convolution? 4. Okay. So if the length of one is, say, length L, in this case 3, and this is length P, in this case 2, what is the general formula of the convolution, the length of the convolution? L plus P minus 1, right? For continuous time signals, you just add up the numbers because it's continuous. But in discrete time, there's this negative 1 you have to take care of. All right, so, okay, so did you get this down? So while I'm saying obvious things, you can continue working on it if you haven't already finished. All right, so what I'm going to do today is two things. So the first thing is, first we'll talk about FIR filter design. What is FIR? By windowing. So we've done a little bit of this in continuous time, but really you design things in discrete time. Okay, so we want to see in a little more detail how we do the design in discrete time. And part 2, we'll talk about DFT, the infamous DFT from 16B. But now when you see it again, it will be so simple. You'll be like, oh, that's it, you know. Why did you give us such a hard time in 16B? All right. Okay, so let's start with FIR filter design. You're not, I'm going to lock the doors before I say this. You're not responsible for today's material, but there's good reasons to pay attention. The first part about FIR filter design is a wonderful way to practice all the properties of Fourier transforms. It's just a perfect exam review, okay, while also adding a little more to what we did before. Part 2, DFT, you want to hear about this somewhere, right? So you might as well stay for that, right? Okay, so for part 1, I'm going to go a little faster. I'm not going to write things down. And there are going to be a lot of figures, so I'll just go to the notes. Frequently asked question, can you post the notes before the class? I would have loved to, but I keep tweaking until the last minute. There is a set of notes from the last time and years ago when I taught this. It's on my webpage. It's all collected. But it might confuse you because I'm doing things in a slightly different way. I'm reshuffling things. I'm cutting off some things. That was a time when students came with the background of 20, not 16. Okay? So there was a lot more overlap with 120, so we were going farther. So now I'm going to remove some things from the old notes and streamline a little bit. So if you really want to look at things before, do it at your risk. Go to my webpage. There you'll see some link to 120 notes, but they're old. Okay? Nevertheless, there are overlaps, of course. Okay, so FIR filter design by windowing, right? So ideally, you want your discrete time filter to give you this frequency response. The DTFT should look like this, ideally, where omega c is the cutoff frequency above which you don't want to pass frequency components, right? The problem, again, is, you know, if you go back to see what impulse response is going to give you this frequency response, and remember, impulse response and frequency response are DTFT pairs, right? So you'll get a sink. And we kind of discussed this in the continuous time case too. There it was also a sink. It's two-sided, not causal. Therefore, you can't do any of this in real time. Okay? So the idea to make it implementable was to A, truncate the sink, and B, move it to the right so that it starts at time 0, the impulse response, right? That way you make it causal, okay? So we'll do similar things here, but we'll take a closer look at what's happening when we do these operations, okay? Very similar to the continuous time derivations that I did quickly, in a little more detail and also adapted to discrete time, okay? So how do I truncate? One way to represent the truncation is to multiply h with what we call a window function, okay? It basically is a function that's 1 between negative n1 and positive n1, and 0 outside of that. So W is graphically something like this. After n1, it becomes 0, and before negative n1, it's again 0. Okay? So when you multiply with h, it keeps the middle of h, truncates what comes after. So going back to my silly octopus analogy for sinc functions, you know, you're truncating the lobes, what do you call them again? Tentacles far away, right? Okay, so what does this do? What does this truncation do in the frequency domain? So in other words, what happens to the frequency response? Well, this is what happens. This is the multiplication property we discussed last time. What happens is that you're going to get a convolution as a result of this in frequency domain. Multiplying in time domain means convolution in frequency domain. In discrete time, the frequency domain is periodic. So it's not the regular convolution, it's a periodic convolution as discussed last time. So it's this operation. The period is 2 pi. All right? So to do this, I already know the ideal response h, it's at the top. I need to know the DTFT of this window function, W, right? By now, you should be very comfortable with this, right? You know, rectangular pulses and sinks, right? So what kind of W do you expect? What kind of DTFT do you expect when it's a pulse like this? It's going to be a sinc, but a periodic version of sinc. So not sine pi x by pi x, but rather sine something by sine something, and that we did in one of the earlier lectures. So here it is as a mathematical expression, and here it is as a picture. So this is W of e to the j omega, as omega goes from 0 to 2 pi. And I guess I made this picture assuming or taking the value n1 equal to 2, I guess, right? Because that's 2 pi over 5, right? So, of course, if you have a larger window length, then you'll have more and more of the tentacles in here, okay? So then what we're going to do to obtain the modified frequency response, h hat, is to take the convolution, the periodic convolution of the thing at the top with this, right? And that's what happens on page 2. So this is just reminding you of how you do periodic convolution. It's the usual thing, not very different from the standard convolution. H stays put, in this case. W gets flipped, but nothing happens when it's flipped because it's symmetric. And it gets dragged by omega. So we switch to the dummy variable theta instead of omega. So this W is dragged by omega, so it's centered at omega, right? So for a fixed omega, you multiply them and integrate over a period of 2 pi, right? So, and then you keep moving it, change omega, and then the octopus starts moving out of that box. So when you multiply them, less area will be there to integrate. So that's why you start getting these ripples, and also you sharply go down to 0. The point where you go sharply down to 0 is when this guy starts moving out of the box, right? As I change omega, I'm just moving this octopus to the right, sliding it to the right and doing the integration that way, right? As it slides out of the box, then we drop back to 0 very quickly. Okay, so this tells you what you get. This is the price you pay for truncating the sinc. All right, so you're not going to get a perfect box. You're going to get these wiggly thing. So that's your frequency response, okay? Now, you might think that, well, that's in this picture, obviously, you took a very small window length, right? That's why I'm nowhere near h. So if I take a large window length in my picture before, like this guy here, if I truncate farther away, choose N1 to be bigger, so I keep more of the sink and truncate less of it, then perhaps I'm going to get much closer to the ideal response. Does that happen? The answer is yes and no, a little ambiguous. Yes, in the sense that you have uniform convergence, as we discussed before. If I sit on a point in the frequency response, if I fix a frequency, I get closer and closer to the actual, the desired ideal response as N1 goes to infinity. However, there are going to be ripples, and those ripples are going to get slimmer, thinner, but they are not going to go away. So the peak amplitude is always the same, no matter how large N1 is selected. Okay? So we saw this type of thing before. Remember what it was called? Gibbs phenomenon. It's again the Gibbs phenomenon. There the context was a little different, but it really is the same thing. The context there was the Fourier series. We had found the Fourier series coefficients for a periodic rectangular pulse. Okay? And incidentally, those coefficients look like samples of a sink, because we know that, boxes, rectangular pulses go with sinks, right? So the Fourier series coefficients look like a bunch of numbers selected from a sink, right? And then we asked, what if we truncate this series, right? We're not going to go to a sub k to infinity, right? We have to stop somewhere. How much closer is the sum of these sinusoidals with these frequencies come close to the actual box? That's where we saw this. So it's the same thing, really. It's dual to what we had seen there. There we were truncating in the frequency domain because we were truncating the frequency component. We were getting rid of high frequency components. And the time domain signal, the periodic time domain signal we were recovering, had these ripples. Now we are truncating the sink in the time domain. And then the box we should be getting in the frequency domain is ending up with these ripples. So really the same phenomenon reoccurring in different shapes and forms. Okay, so Gibbs is a shapeshifter. It just comes in it can pop up in time domain, frequency domain. It's always there. Okay, so is this good news or bad news? Depends on what you're looking for. If you want a good filter, this may not be very satisfactory, right? Because you have these peak overshoots, right? And you may not want that near your cutoff frequency. That doesn't look cool, right? So how do I eliminate this? To eliminate this problem, you need to first diagnose the problem. Why is it that we are getting these ripples that don't go away? What contributes to it? And to see this, you have to look a little more closely at the convolution operation you're doing in figure 1, right? I mean, the mechanics of convolution you're familiar by now, and you're multiplying these things, integrating, and all that, right? So what is really the root cause of these oscillations? Again, you have to visualize what's happening when you do convolution. You slide this octopus, right, which is centered at omega in the theta axis. So you slide your omega, the center, and you do this integration. Why are you getting these oscillations? Yeah, the tentacles are coming in, going out. It's the tentacles that cause these oscillations, right? So, and if I go back and look closely at this Fourier transform, look at the blue one, right? The reason for these oscillations, the Gibbs phenomenon, is that we have two prominent tentacles here, so to speak. Okay. So why are they so prominent? What is it that puts so much meat? It's getting sillier and sillier, this comparison. But anyway, what makes this so much more pronounced? So what puts so much weight in these ripples of this guy? So you have to go back and think about the time domain signal. It was the window, right? This rectangular pulse, which we use as a window function. And this blue guy is the DTFT of that, right? So what feature of that discrete time signal, the window, makes these so pronounced? I guess this is centered at omega. Let's go back and look at the, this is the same thing basically for n1 equal to 2, okay? So this is called the main lobe, and these are called the side lobes. What I call tentacles are really the side lobes, okay? So the problem we know is that the side lobes have too much area, and those areas contribute to these oscillations when we do the convolution, which involves integration. So, but if you look at the signal, it's this. So, you see this is pi, right? What is pi in the discrete time frequency domain? The highest frequency, right? So this has high frequencies, pretty strong high frequencies in it, right? Now go back to the time domain signal. What is it, what do you think is giving it so much high frequency content? Any abrupt change excites high frequencies, right? To reproduce a sudden change, right, you need to think of the Fourier series even, right? To reproduce any sharp change, I need to go to really, really high frequencies, right? So that's the reason. So this guy is 1, and all of a sudden decides to be 0, and that sharp change is aggravating the high frequencies in its Fourier transform, right? If the purpose is just to truncate, why do we truncate so abruptly? Why don't we just taper, towards the ends, and then slowly ease into 0 rather than, keeping a chunk of it and then cutting off everything else, right? If we did that, then what we are doing here, the multiplication of h with the window, so the window would be a smoother window. We could design what we call a tapered window, right? The one that smoothly goes to 0 rather than sharply. Then this will change. This will put more weight into the low frequency. And that will cause those ripples to diminish. All right? So that's the main idea. The diagnosis of these ripples, Gibbs phenomenon, is that the truncation we did is too abrupt. We multiplied with this very sharply changing window function, and that's creating these ripples. The remedy is to use a truncation that smoothly goes to 0, more smoothly than this. Okay? In other words, define a different window function, not a rectangular one, that has smoother features, that goes to 0 more smoothly, thereby giving us less content in high frequencies. So that's the idea in what's called tapered windows. A bunch of people came and defined their own tapered windows. There are a bunch of names involved in this. And they all look alike too in some sense. So one of the well-known tapered windows is the so-called rectangular one. This one is simple. It's the black one here, right? So this person, whose name must have been Bartlett, because these windows are also called Bartlett windows in addition to being called triangular, said, this rectangular window function has too many high frequency components, so let me just use a triangular one. That's smoother, right? We actually saw the Fourier transform of a triangular thing, right? It amounts to sinc square, essentially. And when you looked at the picture, they sharply went down, right? The side lobes were much lower because you're squaring small numbers, right? So that was one idea, okay? And the others who wanted to attach their names to something came and invented other types. So they have funny expressions involving sines, cosines, etc. So I'm not going to give the expressions. The plot should give you enough of an idea. One of them is called the Hamming. According to my legend here, the green one is the Hamming window. The blue one is called the Hanning window. I think that's some kind of insider joke. I think Han, H-A-N-N, was a name. So they called it Hanning, meaning apply Han to, I don't know, it's just silly engineering jokes, I guess. So that made it similar to the other name, which is actually Hamming. Okay? And then Blackman is what? I don't even remember Blackman. Bartlett is the triangular one. Anyway, so you may look at these and say, what on earth? You know, they all look alike. At least perhaps not the triangular one, but the other three. Right? So why would you invent things that look alike? You know, why do you need so much of a variety? Well, in fact, if you look at their Fourier transforms, they are quite different. Things that may look similar in time domain may have subtle differences that are not visible to your eye, that only become visible in the frequency domain. So if you look at their Fourier transforms, you see bigger differences. So these are the Fourier transforms of all these windows. The one at the top is the usual rectangular one. And we are using a logarithmic scale here. You know what? Let me first zoom into the first two. Okay? Rectangular versus triangular. Okay? And these are the frequency responses given in a log plot. Okay? When do we use log plots? When we want to squeeze a lot of information in there, right? I mean, so these numbers is like negative, I can't even see, negative what? Negative 10 dB. These are like really small numbers. If you plot them on a linear scale, you'll just like the time domain plots we just looked at, they'll all look similar because they'll go down to zero very fast, right? But here you can have a clearer comparison, magnifying basically the smaller numbers. So what's happened here is when you use the triangular window, the side lobes, the tentacles went down considerably, right? From negative 10-ish dB decibels, it went below negative 20, right? So that's a significant drop. So the triangular window brings down the high frequency content considerably. And the others do an even better job. You see Hanning compared to the triangular, and Hamming somehow has a more flat amplitude for the side lobes. And then Blackman is probably the best. Look, the biggest side lobe is like negative 60 dB, right? Doesn't get much better than that, okay? So these guys were able to create their own octopuses or octopi with smaller tentacles, and that did the job, right? So that's the main idea. But when you look at these plots, you certainly see an improvement in terms of pushing down the tentacles, okay? So, and that will reduce those ripples that we see in the Gibbs phenomenon. It will not necessarily eliminate them altogether, but you'll have much smaller ripples. That gives you better quality of filter. But then you should see a trade-off if you look closely, if you compare them. What is happening that looks, you know, what, in addition to the side lobes going down, something else is changing as you go from the top to the bottom. So that's like a little price to pay for pushing down the side lobes. Yeah, the width is also getting wider. Okay? Why is that a bad thing? So this is a compromise here, right? So there's a trade-off. You push the tentacles down, but you get a larger width of the main body of the octopus, right? So why is that a bad thing? Let's go back and look at the picture of our convolution again, right? If I have smaller ripples here, but a more pronounced main body, what kind of effect would you observe when you do the convolution? Yes. Right, less steep, right? So look here, the drop happens quite fast. Why? Because there isn't so much area in this, right? So when you move this guy to the right, quite abruptly, it'll move out. And all of a sudden, you have much little area left inside the box, right, to integrate. But when this becomes wider, when this main body, main lobe, becomes wider, it will take a while for that octopus to leave that box, right? So that will lead to a slower transition. Okay? So there are two factors in your window design. One, you want these side lobes to be of small amplitude to get smaller ripples out here. The second concern is to make the width, keep the width small so that you have a sharper transition. So there's a bit of a trade-off between sharp transition and those ripples. So if you want sharper transition, you're going to get bigger ripples, essentially. And we saw that clearly in comparing those windows, okay? Those that give you smaller ripples, the ones at the bottom, also give you a slower transition. Yes? The x-axis is frequency. It's normalized to 1, so 1 you should read it as pi. Okay? So going from low frequency to high frequency. Of course, it's periodic and there's conjugate symmetry, right? So this is pi, and then if you put a mirror here, right, this mirror image is going to be from pi to 2 pi, and the rest is just periodic. Discrete. This is the DTFT. Okay? So that's the idea. You can read these notes. It's just a cute illustration of all the Fourier transform properties and why people care about these things. So to summarize, if you want an FIR filter that approximates the ideal filter's impulse response, frequency response, you take the sink that gave rise to the ideal low-pass filter, you truncate it. But you don't want to do it necessarily with a rectangular window W. You can choose one of the various windows we discussed, the tapered windows. And that way you're going to get an impulse response that's of finite duration. Still symmetric about n equal to 0. And then you shift it to the right so that it becomes a right-sided signal, making this a causal system, therefore appropriate for real-time implementation. You can process data as it arrives. You don't have to know what's coming next. Okay? So the effect of the time shift to make it causal is basically multiplication with e to the negative j omega n 1. That's the time shift property of DTFT that we discussed last week. All right? So one more thing to do here. So this sink is such that, okay, I guess this is a semi-review lecture too. So one thing to note is that, so we have the sink. Let's go back to our first slide. Omega c by pi, sink whatever, and it gives us this response, right? So let me ask you a question, examish question, although that probably won't be on the exam. Okay, so what was it? Omega c by pi, sink, omega c by pi n, was that it? And it gave us this DTFT, right? 2 pi. And that was the cutoff. And this was 1, important. This is 1, right? So if I ask you, what is this sum? Okay, let me just put everything inside. What is this sum from n negative infinity to infinity? By pi, sink, omega c by pi times n. Are you going to really sum it from negative infinity to infinity, or are you going to be smart, the way you should be in the exam, and leverage all these useful properties of DTFT, CTFT we discussed, right? Is there a quick way to recover this sum by just looking at the DTFT? So the frequency response at 0 frequency, right? Just think of the synthesis equation. Or no, just the analysis equation, right? If I had e to the negative j omega n here in this sum, I would be getting this guy, right? Yes? If I substitute omega equals 0, then this just becomes 1, and you get what I was asking you, right? And that is the value at omega equals 0, which is 1. So you can read off this from this number, right? The dTFT at 0 frequency is really that sum. Yes? Okay. All right, why am I asking you this? So this is the ideal response, H, ideal impulse response, H of n, right? And it gave us this ideal frequency response, H of e to the j omega. Now I did all kinds of things to this octopus. I truncated it, I abused it, right? So do I still, when I sum those numbers after I do these, so H hat of n was H of n times the window, right? If I sum H hat of n from negative infinity to infinity, is that still 1? No, why should it be? I mean, let's say we're just truncating it, right? A chunk of it is gone. It will add to something less now, right? And if you're using tapered windows, it will be farther different, right? So, but, you know, this is a low-pass filter, so I want to make the gain at low frequencies close to 1, and ideally equal to 1 at the 0 frequency, right? So after doing all of this, I should calculate this number, right? And scale everything I found by this number so that the sum is still 1, right? So if I call that, say, I don't know, k, right? Then I should really use a filter with coefficients not h hat of n, but h hat of n by k. So that way, the new one, the scaled one, sums to 1, and therefore we get a gain of 1, right? So there's that little minor step one has to worry about. That's why I made this little detour here. So that's what the summary said at the end. Where's my summary? Yeah. So that's what it means here. Finally, h hat of n must be scaled by a constant to obtain sum equal to 1. So the DC gain means the value of the Fourier transform at omega 0 is equal to 1. Okay? So in the end, this will be a finite length impulse response, causal because we shifted it, and therefore we can implement it as an FIR filter. It will have this form, and those coefficients, B0, B1, etc. of the FIR filter will come from what we designed for our H hat after the scaling, of course. This assumes the scaling has already been done. Okay? So that's a summary and also a quick review of Fourier transform as a byproduct. Do you have any questions? Yes. Say it again. Oh, good question. All right. So, okay. Well, start with this. Okay. I give you this filter. It's like a difference equation, except that there are no y of n minus 1 types of terms, only x's, right? So what is the impulse response of this? Great. You guys turned this into exam review. Perfect. So I give you this. I ask you, what is the impulse response? How do I find the impulse response? I apply an impulse and see what the response is, right? So applying an impulse means, you know, x is delta, right? So this guy here is B0 delta of n, right? This is B0. What is this guy? It's a delta centered now at 1, right? So B1 elsewhere equal to 0. And this is centered at M. Everything else is 0, right? So if I add them up, I get h of n, which is the response to deltas. That looks like B0, B1, B2, Bm, and it stops there, right? Okay? So those coefficients that you see in an FIR filter expressed as a difference equation really are the impulse response coefficients. That's why FIR filters are so nice, because everything is so easy, right? The moment you add a little feedback, if it was like y of n minus 1, you're going to get an infinite impulse response. There won't be a simple mapping of the coefficients. Did everybody follow this? Everybody's good with this? Okay. So, all right, so I think that's good enough. Any other questions? All right, if no, let's take a short break now so you're ready for the next part, which is DFT. And while you're doing the transition, I'm going to add another question here for you. If you didn't do this, you should do it now, okay? But here's the other question. Part 2 of my question, which for now, pretend they're unrelated, but in the end I might, if I have time, I will relate them. Here's my question. Let Q of S, define this polynomial to be alpha 2 S squared plus alpha 1 S plus alpha 0. And define another polynomial, R of S, beta 1S plus beta 0. Find Q of S times R of S. Do it. Forget about the upper part. Just do this. You're going to get something times, what's going to be the order of this polynomial? Yeah, so you're going to get something times S cubed, right? Plus something else times S squared plus something times S plus something, right? Do it. And forget about the convolution. And at the end, look, you can compare them for fun. Huh? Oh, okay. Okay, so, some of you saw this in 170 algorithms. Why did they do that? Because they want to tell you about FFT. FFT is an algorithm, a fast algorithm for doing DFT, right? You don't just, we didn't discuss DFT yet, but you'll see it in a minute. So FFT is an algorithm, and of course these CS theory guys love it because it has all the order of whatever notations they love, and you know, is it P, MP, smoke pot? Anyway, so so they want to tell you about the FFT, but they didn't do DFT, right? They had to find a way to ease into, you know, a meaningful context for FFT, and something that, you know, students who haven't taken 120 can relate to. Polynomials. Everybody loves polynomials. Okay, so we'll come back to this hopefully if I have time at the end. Yes. Okay, so we start a new discussion, DFT. Discrete Fourier transform. Well, first of all, we saw discrete time Fourier transform. Now, what is the discrete Fourier transform? What is DTFT versus DFT? The difference is the DTFT itself is a continuous function of the frequency. It's periodic with 2 pi whatnot, but it is, the fact remains that it's a continuous variable omega. Okay? When we talk about DFT, it is itself discrete. Okay? So that's perhaps the most high-level bit that you should remember. DFT, discrete in the frequency domain, and DTFT is continuous, even though we apply both of them to discrete time signals. Okay? Continuous in frequency domain. All right? And we'll come back to the connection, and you'll see, that's so nice. It's very, the connection will be very clear. Okay? So, but before that, DFT means discrete Fourier transform. Discrete Fourier transform. It is applicable to finite duration signals. Okay? So we have x of n. It's a sequence, basically. I give you a sequence of numbers. I can ask you about the DFT of that. I don't have to tell you it's time domain, x of n, whatever. I can give you just a few numbers, ask you what is the DFT of this, right? So x of n, as a convention, since it's finite length sequence, we're going to label it with an index little n. And as a convention, we don't care where time starts. We just say it starts at 0 and ends at n minus 1, so that the length of the sequence is capital N, okay? Length n sequence, okay? So that's the given. I give you the sequence. I ask you, what is the DFT of this? The answer is another sequence of length n, except that it's in the frequency domain. I will define it in a second, okay? So discrete Fourier transform DFT of a length n sequence defined this way is itself a length n sequence. We'll use the capital X as we always do when we do transforms, because after all, this is a transform itself. And then since it's also length n, I'm going to label it with index k and go from 0 to n minus 1. It's only convention that we go from 0 to n minus 1. If you want, you can start 140 and end at 140 plus n, okay, minus 1. So completely your call. But we'll stick to this convention. So is a length n sequence defined as follows. Now things will start looking reminiscent of things we did earlier. X of k is the sum from 0 to n minus 1 of x of n times e to the negative j 2 pi by n times kn. Okay? If I fix the k, you add these n numbers, and it spits out a number. That's your x of k. And I do this for k 0, 1, 2, and minus 1. So I have a sequence of length n. Okay? So I think it's good to understand the mechanics before we question the relations to other Fourier transforms. So the point is that I give you a length n sequence. It's DFT is another length n sequence. FFT computes the DFT. It means fast Fourier transform. It's a fast algorithm to do this operation. Doing it by a brute force application of this definition has a lot of repetitions. There are a lot of symmetries hidden in here. Okay, so FFT basically takes advantage of the inherent symmetries and does faster computations. And because it's so fast, people call it fast Fourier transform. So DFT is really synonymous in terms of what it does with FFT. But keep in mind, FFT is just an algorithm to perform DFT. So FFT is an algorithm to find DFT. Okay? So any numerical software, algebra software like MATLAB or Python will have a command for FFT. Most likely it will be FFT. Is that true for Python? So if I tell you, what is FFT of, I don't know, 1, 1, 3, 4, I gave it basically length 4 sequence. I can't do it off the top of my head, but it will give me 4 numbers as a response. And most likely they'll be complex because such are Fourier transforms, just to make our lives harder. Okay? Okay, so that's the important part. You get a sequence in the frequency domain. And if you look at this, this looks awfully like some of the things we already did, right? Like, what does this remind you of? What else did we learn? We are dealing with a discrete time signal, a sequence, right? So in discrete time, we've talked about Fourier series and the Fourier transform, which is DTFT, right? This guy is related to both, closely related. Let's first see the connection to the Fourier series. Fourier series is applicable when your signal is periodic. Here we're talking about a sequence of finite duration, so there is no periodicity, right? But I can take this, copy, paste, 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 and get a periodic signal, right? And then what I'm doing here is basically doing this operation to one period of that periodic signal, okay? So I'll leave this as a question to you. While I'm writing, think about the answer. How is this related to the Fourier series of a periodic signal x tilde of n that I'm going to define as follows: x of n modulo capital N. What does this mean, what I wrote here? When little n exceeds capital N, it reverses back. So it basically creates the periodic signal, the copy-paste that I was just telling you about, right? It does that. So it's just a fancy way of writing it with modular arithmetic, okay? So what matters is that x tilde of n is now periodic with period n. And if I look at this x tilde at times from 0 to n minus 1, it is identical to my finite length sequence, right? But now I can apply the Fourier series definitions to it. So what does it look like, this summation here? It looks very much like the analysis equation from which we computed the kth Fourier series coefficient, correct? But there is a factor. We used to divide by the period, right? So recall AK for this periodic signal, AK was 1 over n and 0 to n minus 1 x tilde of n e to the negative j fundamental frequency, which is 2 pi by n, times k times n. Am I doing this right? And in this interval, from 0 to n minus 1, x tilde is the same as x, right? So what I have here is then the same as what I just defined, x of k, right? So this tells me, other than this factor, this division by n, I'm really looking at the Fourier series coefficients of the periodic version of my finite duration signal. Okay, so to summarize what we just showed, the kth DFT coefficient is the Fourier series coefficient AK for periodic x tilde constructed from x as x tilde of n, what I just wrote before, x of n mod capital N. Okay? So the moment we covered Fourier series, we are actually pretty much done with DFT. We also have a way of, yeah, what am I missing? N times AK, right? Something's wrong here. N times AK. Okay, for periodic x tilde. Okay? So other than this factor n, it really is the same as the Fourier series coefficients. And because of that, we can also derive a synthesis equation to recover the signal from the DFT coefficients xk. And to do that, I just don't need to do anything because I already did all these things for Fourier series, and now I know the connection, right? What was the synthesis equation for DFT? I'm sorry, Fourier series synthesis. It's the series itself, right? X synthesis. This turned out to be a great review session for the exam too, right? So synthesis equation was x tilde of n. What do you do? Sum ak e to the j 2 pi over n kn, right? K negative infinity to infinity. These are all the frequency components, right? That's how we construct x tilde. That's the definition of the Fourier series itself, right? You take your signal, decompose it. What am I doing? No. So this is discrete, right? So you don't go to infinity, really. You go from 0 to n minus 1. That's enough, right? Because in discrete time, remember that was the big difference of Fourier series between continuous and discrete. In discrete time, you only need n of these basis functions. They repeat themselves anyway, so you don't go to infinity. Okay? Therefore, convergence and all these things were non-issues for discrete time signals. Okay, so then this should give us a way to obtain x, little x of n, from x of k. What should be the relation? Well, remember, AK is, through what I said here, n times AK is x of k, right? So then AK is equal to 1 over n x of k. So if I put a factor of 1 over n here, then really what I've written inside is similar to AK, right? And then you have e to the j 2 pi over n kn. Okay, so that gives you x tilde. But again, x tilde and x are the same when I look at n equal to 0, 1, to n minus 1. Beyond that, x tilde repeats. X doesn't because x is finite duration, so that's why we define the synthesis equation only for these values of n. Okay, so that's our synthesis equation, and this is our analysis equation defined for k 0, 1 to n minus 1. Okay, very simple definitions, and the connection to Fourier series is straightforward, almost identical. The one main difference is that the division by n happens in the analysis equation in the case of Fourier series. It comes into the synthesis equation in the Fourier transform, DFT. Okay, so let's look at an example. Any questions before I move on? Okay, good. So, first example. Let's say we have a signal that's a simple pulse. started at time 0, lasted for 5 units of time. Since it started at 0, the last time was 4, and afterwards it became 0. Okay? So finite duration signal with duration equal to 5. In other words, n goes from 0 to 4, right? And let's say the value is 1. Okay? So let's find the DFT. DFT will have 5 numbers in it, because the signal is a length 5 sequence. Its DFT is a length 5 sequence. Only we may get complex numbers or not, depends on the signal. Okay? So let's do it. Remember the definition. You will have to sum from 0 to 4 x of n e to the negative j 2 pi over capital N, which is 5, kn. What is 2 pi by 5? 372 degrees. Is that right? Something like that? 72. Okay. All right. So what is x of... So this is capital. Let's not confuse the with the little x. So this was little x of n, and this is capital X. So what is capital X of 0? Well, k is equal to 0. Well, first of all, for any k, these are always 1 in this interval from 0 to 4, right? From 0 to 4, it's always 1, so we don't have to worry about that x, right? We're really adding 0 to 4, e to the negative j, 2 pi by 5, kn. But if k is equal to 0, what am I really adding? They're all 1s, and I have 5 1s that I'm adding, so it's just 5. Okay? What about x of 1? Now, each one is a complex number. Okay? So, we fix k equal to 1. We fix k to be 1. So, we're looking at these numbers, e to the negative j, 2 pi by 5 times n. For n equal to 0, that number is just 1, right? But I'm going to draw it in the complex plane. Okay? For n equal to 0, e to the negative j, 2 pi by 5, n looks like this. For n equal to 1, it is going to be, it always is going to be on the unit circle, because e to the j whatever has magnitude 1, right? Yes? Okay, the phase, though, is now negative 72 degrees. So it's something like, I don't know, 72, something like this. So this is where I go at n equal to 1. Okay? So this is like a clock that ticks by 72 degrees at each instant of time. So then I'll have 144 for n equal to 2. And then 144, how many more to 36, another 36. So it's actually symmetric with respect to this. So I think these two angles are the same, this and that. So this is n equal to 3. N equal to 4 will be symmetric to this guy, because it's going to be like 72 degrees here. And these are both 36 degrees, right? Anyway, so I have these 5 numbers, 5 complex numbers that I need to add to find to find this, right? What would I get? It will be 0, because they're all 72 degrees apart from each other. They're all pulling someone with opposing forces that add to 0, right? If I was looking at x of 2, what would happen? Then I would put 2 here. So now I would be looking at increments of 144 degrees. So if I were looking at k equal to 2, and 0 would still look this way, and 1
would be 144 degrees, and 2 would be this guy, and 3 would be back here, and 4 would be back here, right? Really, you get the same vectors after all. Just different ends correspond to different ones, but it's the same 5. So they will all again add up to 0. So really, k equal to 0 was an exception when they didn't cancel each other out. For all other k's, you get these opposing things that cancel out, and you get a sum of 0. Okay? So the answer is x of k equal to 5 when k is equal to 0, and 0 when k is equal to 1, 2, 3, 4. We don't go beyond that because this was a length 5 sequence, and the DFT itself is a length 5 sequence. Okay, questions? And we are lucky in this example because we just got real numbers. That's not always going to happen. So you would call this a 5-point DFT because the length was 5. And we applied the definition with n equal to 5. Okay? Yes? No, we usually define it as a finite sequence. I mean, if you really wanted to define it for all k, you'd make it periodic. But at that point, you're really talking about like Fourier series of a discrete sequence. So yeah, let's for DFT stick to finite length things. Okay. Okay. So now this signal x, little x, was length 5. But a length 5 signal is also a length 6 signal, right? Or length 7 signal. I could have taken n to be anything bigger than 5, and I can still apply the definition. The only difference will be that I'll get more numbers because the definition gives me n numbers back, takes in capital N numbers, returns capital N numbers, right? I can enter, even if my signal is length 5, I can take a 10-point DFT, meaning that the first 5 numbers in my sequence will be what they are, and the rest I'll be just planting zeros, right? So what I can do basically is take these guys into account. Let's say I put 5 more, right? And then I can apply the definition of DFT with n equal to 10 to this sequence, including the zeros. And then x of k will all of a sudden be 10 numbers and quite different from these 5 numbers we derived. Okay? So let's do this in this example. Okay? So let's take the 10-point DFT, which simply means we're going to take n to be 10 for the example above. Okay? So then the sequence we provide to MATLAB or Python, whatever you're using, would be FFT. It was 5 ones, right? But if I want a 10-point DFT, I need to pad 5 zeros and make it look like a sequence of length 10. And you hit return, and now you get 10 numbers. Okay? So from k0 to 9. Right? That's how DFT works. So let's do this for this example. So these calculations, if I just apply this definition with n equal to 10, that's fine, but it's going to be quite messy. So what we can do instead is we can remember the connection to the Fourier series, right? Taking the 10-point DFT of our signal, which was simply once for a period of, for a length of 5, ending at 4, and we padded 5 zeros, right? So taking the DFT of this length 10 signal is the same as finding the Fourier series coefficients of its periodic version, which I generate by a simple copy-paste. So I just make it periodic this way. And then on the other end as well. 2, 3, 4, 5, etc., right? So this is our x tilde of n. Okay? So instead of, there's nothing wrong applying the DFT definition and going through the algebra, but I'm practical. If I did a Fourier series example like this, I'm not going to do all the math again, right? We already know the connection to Fourier series, so we can leverage that, okay? In fact, in lecture 5, we saw this example. Lecture 5 was this example, a periodic pulse, values equal to 1, and these are 1, 2, of course, up to n1, and then zeros, it repeated with period n. And we found that for this periodic pulse, we get Fourier coefficients a sub k that look like the following. It was sine ak was equal to, we're doing review, right? What is ak for a0, for k0? Oh, okay, you guys are ready. Okay. 2n1 plus 1 by n. Basically the average over one period, right? Okay, for k equal to 0. Okay, and then when k is different than 0, a little bit of algebra showed us sine. Are you just reading from the notes or are you reciting from memory? Oh, good job. Okay. Good, you're ready. Okay. Sine pi over 10k. What am I? Okay, sure. All right. So, no, it's a longer expression than that. When I substitute, I want to make this look like that, okay? Yeah, sorry, guys. Okay, so there's a messier expression in lecture 5 because lecture 5 is for a general n1 and general n. But in our case, n1 is equal to 2, right? Because we have length 5 pulses. And n is equal to 10. And after I substitute those two numbers in lecture 5 notes, I get these numbers. And of course, this should simplify as well, right? 5 by 10, 1 over 2, right? Okay. So that's 4k equal to 1 to 9, all right? And of course, Fourier series coefficients are periodic. We only need 10 of those, so those are the ones, all right? Are we all good? Okay. Now, are they the same though? What's the difference? It's shifted, right? So, shifted by how many time units? Shift by 2. What happens to these guys? Multiply by, louder please, 2 pi over n, which is 10. I shifted by 2 units, right, times k, right? So ak becomes this times ak, right? So really this should be multiplied. These should be multiplied by this factor. So 4 pi by 10 times k, all right? So doing that, I now have an expression for xk. So this was our x of n. So x of k, by leveraging the connection to the discrete Fourier series, all we have to do is multiply by n, right? So 10 times ak times, so I guess I reserved ak for the unshifted thing, right? So 10 times ak times e to the negative j, 4 pi by 10 k, okay? So that's what the coefficients are. And ak are given here. Okay? If you do this, you find the following numbers. x0 is easy. What is it? This is just 1 in that case, right? This guy is 1 when k is equal to 0. So 1/2 times 10, 5. The others are less easy. And I'm going to give you a couple of them. For example, here are some easy ones. X of 2, X of 4, X of 6, X of 8. Somehow they're all equal to 0. X of 1 is 1 minus j, 3.077, a bunch of 7s. And then, okay, x of 9, I'll need this later, so that's why I'm writing it. It is 1 plus j, the same number. Okay? And x of 5 is 1. X of 7 is a complex, something messy like this. It's a complex number. But x3 is the complex conjugate of that. So the takeaways, I guess, are that x1 and x9 are complex conjugates, and x3 and x7, which I'm not writing, but they're in the notes, are also complex conjugates. Is it coincidence why these are complex conjugates? Huh? Yeah, I want to see that, but okay, let's think about it. So put k5 there, right? 5 pi not sure. So okay, if I put k equals 5, I'm talking about in the numerator 5 pi by 2, right? That's pi by 2, 1. Yes. And then the denominator is 1. Okay. Quite likely you're right. Yeah, I need to check that a little bit. Okay. Oh, but wait. Here it is. Well, you caught something indirectly. I think we had a factor here that is missing. Yeah, there was a 1 over n here. Remember, this was 2n plus 1 by n, the one at the top. This also has a division by n. Now we are clear. Okay, so it is actually 1, and it's cancelled out. Thanks for catching that, though. Okay, so anyway, so the point is, for the same signal of duration 5, I can also do a 10-point DFT. I can do a 100-point DFT. It's my choice, right? But I'm going to get different numbers. These numbers here look nothing like the 5-point DFT numbers, which were all 1 or 0, right? They are different. So in general, you'll get different numbers. But in this example, we saw this complex conjugate property. So this is a general property, in fact. True in general when x is real valued, you'll have x of n minus k equals x of k conjugate. Okay? This is a consequence of a very similar property we had for the Fourier series, so I'm not going to derive it again. All right? But when you're looking at DFT coefficients where the indices add up to n, you should be getting complex conjugates, and that's exactly what happened in our example. 9 and 1 added up to 10, which was our capital N, so they are complex conjugates. 3 and 7, which I didn't write, add up to 10, so they are complex conjugates. Okay, so that property is always there for real valued x. All right. Okay, so I think you understand the mechanics of DFT You also understand the connection to the Fourier series, therefore you understand more than mechanically. You kind of understand DFT now, right? So now let's connect DFT to DTFT. And everything will be connected then between DFT and DTFT. Remember, the big difference between those is, what did I say at the beginning? DTFT is a continuous function of omega. DFT is itself a discrete thing, right? When we say connection, the connection has to account for one being continuous, the other discrete, right? And it will. So let's recall how we defined the DTFT. It was n negative infinity to infinity, x of n, e to the negative j, omega n, and that was it, right? Now, I'm dealing with an x of n that is of finite length. It starts at n equal to 0, ends at n minus 1, right? So that means this is equal to the sum from 0 to n minus 1, because outside of this interval, x is 0 anyway. So that's our DTFT. Okay? Now, how did we define DFT? We said x of k is equal to sum 0 to n minus 1, x of n, e to the negative j, 2 pi by n, k times n. Now, you don't have to be a genius to look at both expressions and tell me the connection. They kind of look similar, don't they? What is the difference? I have omega here, which is my continuous variable. And here, I have 2 pi by n times k. Other than that, they're identical. Okay? So, what's your answer? X of k is what? It is samples of the DTFT. You look at the DTFT which is continuous, sample it. Evaluate it when omega is 2 pi by n times k, and that's your DFT. Okay? Simple as that. And of course, this accounts for one being a continuous function, the other being discrete. Okay? So really, I wouldn't even say DFT and DTFT are very different things. You know, DFT is something more numerical, right? If I give you a long sequence, and if I ask you to do, I ask you what is the DTFT of this, how are you going to do that? You know, apply the definition, manipulate these omegas. It's a mess, right, in general? I mean, we give you simple examples, so you can do it in the exam, within the duration of an exam, right? But if I give you a sequence with 10,000 entries in it, you're not going to go write this expression at the top and find the neat expression as a function of omega, right? But you can do this numerically. I mean, the DFT. You just go type FFT. These are so fast, you can enter whatever length, the answer will come in no time, okay? So I'm essentially doing some kind of DTFT by doing this. I'm getting many, many samples of the DTFT. So if I get many of them, then I'll get this thing that looks like the DTFT itself. I'll have lots of samples of the signal, okay? So essentially, DFT is a numerical way of finding the DTFT, finding samples, enough samples of the DTFT, further enriched with the algorithms called FFT. There are a slew of them, but they are very efficient algorithms. Okay? So we connected everything. Fourier series, DFT, DTFT, everything is connected. Okay? don't look too happy, but yes. I mean, you can, but you can just as well work with the samples. Is there any reason to do it? There can be. I'm not going to make up one right now. I'm sure if I thought harder, I would come up with a reason. Okay. Are there other questions? Yes. Yes, I'll come back to this. Patient. Okay. Yeah, I think I'll have time to come back to it. Okay. So now let's think about our example. We have this pulse of length 5. We found the 5-point DFT, and then we found the 10-point DFT. They look nothing like each other. There was no obvious connection between them. But there is a connection in the sense that they both come from the same DTFT, right? According to this, the 5-point pulse has one DTFT. When we calculated the 5-point DFT, we just took 5 samples out of it. When we calculated the 10-point DFT, we took 10 samples out of it. We just have more samples, and the samples don't necessarily coincide with each other. Some may. I think, in fact, some did. So let's see this, and this example will connect everything. So DTFT of our example, which is these 5 ones and all zeros, is something we probably did somewhere. Now I'm not going to be able to refer. I did this, I know. Maybe, okay, when I did all these examples, I was cheating, making my life easy, centering everything at 0. Again, this is exam preparation sort of, right? Why did I put everything centered at 0? It's even symmetric, so you get a nice and real valued Fourier transform. That was to make it good for myself, right? Am I going to do that to you in the exam? No. I'm not going to center anything. So better get used to these e to the negative j terms. Okay, so in this case, it's just a time shift to go from, I mean, the centered, you can do the centered one shift by 2, right? So x of e to the j omega from lecture whatever, I don't remember, probably last week or the one before, is this sum 0 to 4 e to the negative j omega n, which if you do the math, comes out to be e to the negative j 2 omega. Guess where this comes from? The shift. 5 omega by 2 divided by sine omega by 2. This is what we did just at the beginning of this lecture. This W of n, remember the rectangular window? And then we had to shift things and stuff. Yeah, it's that. Okay? So it's like the periodic version of the octopus, right? So it's this. For omega equal to 0, we have to make an exception because this is not defined, but it's the limit of that, which is, I think, 5. When omega is 0, and that when omega is different than 0. And I realize the notes are wrong. 5 when omega is 0. Okay. All right? Now, that's a sync-ish thing, so let's go to the note so I don't have to draw it again. Damn it. Okay. Here's the DTFT in the background. All right, so I'm just showing you the magnitude of that because it's not centered, it is complex, so it's easier to look at the magnitude, which is nice and real and positive too. Okay, you kind of recognize the periodic sink there, right? Periodic version of the sink. So that's our DTFT. When I said at the beginning, let's find the 5-point DFT, that really meant I was taking 5 samples out of it at values omega equals 0, 2 pi by 5 for k equal to 1, 2 pi by 5 times 2 for k equal to 2, and so on. So these values that I marked with a blue, those samples happen to hit the sink at the points where the sink was crossing 0. That's why I got a 1, no, I got a 5 rather, here, and then I got a bunch of zeros. Did I mess up when I said, yeah, I said 5, right? Or did I mess it up? When I found the DFT of this signal, 1, 1, 1, 1, 5-point DFT, did I say x of k is equal to 5 for k equal to 0? Is that it? Okay, good. So I didn't mess up anything. Okay. Somehow I thought I put 1. Anyway. Okay, so that was the 5-point DFT, the blue samples. What does 10-point DFT means? It means take 10 samples. Now, apart from each other by 2 pi by 10. So I'm taking more samples, but every other sample actually hits one of the previous samples, because the first one was n equal to 5, the other is n equal to 10, only because it's a multiple of it by 2. Every other one will match. And that's why you got, when I gave you these numbers, remember all the even numbers were 0? Because those even numbers actually match the zeros here, right? So anyhow, that's the important picture. So DFT really amounts to taking samples from DTFT. If I pad, 2,000 zeros at the end of this 5-length sequence and do a 2005-point DFT, I'm going to get a whole bunch of samples out of this, right? I'm going to practically get the sink that's lying behind it. Okay, so that's the point of the DFT and its connection to DTFT. All clear? Yes? Okay. One last thing about why DFT is so cool. DFT first allows you to do DTFT, basically find many samples, essentially finding the DTFT. Another thing is how it saves you from convolution. If you hate convolution, which is too bad because you are sure to have a convolution problem, okay? Could even be a graphical convolution problem. Don't underestimate that, okay? So DFT makes convolution super easy. Okay, one reason, yet another reason to be excited about DFT. So why is that? So let's say I have a pretty long filter, h of n, okay? And I had a long input too, and I need to find, I have a long sequence. I want to filter it out, it's noisy, there are outliers, etc. But I have a good filter I designed maybe using the methods from the beginning of this lecture. So I have a nice impulse response H for it, finite length FIR filter, right? And what is the output, right? I'm applying the input, now I want to get the output. I want to filter my data, right? Basically, I'm trying to do this operation. It's not a pleasant operation, convolution, right? It's a lot of things. So y of n, the output is this, right? How can I do this in a simpler and computational way without dragging, shifting, flipping? You don't want to do any of that, right? Well, remember first of all what this means in the frequency domain, in the DTFT. If I'm taking the convolution of two discrete time signals, what can you tell me about their DTFTs? H of e to the j omega times x of e to the j omega. Now, if I take samples of both sides, the samples on the left-hand side will give me the DFT coefficients of y. Okay, the samples on the right-hand side will give me the DFT coefficients of h multiplying the DFT coefficients of x. Correct? So that means I can just take the DFT of h, take the DFT of x, multiply them. That gives me the DFT of y. Do an inverse FFT, you get the result of the convolution. Easy, but be careful. I went a little too fast. So when we made this connection, remember, I made this important assumption that outside of 0, the interval from 0 to n minus 1, x of n is 0, right? It's finite length. Moreover, I selected my n when doing the n-point DFT to be bigger than the duration, at least the same as the duration, right? That assumption is critical in making this connection, okay? If I take the 4-point DFT of a length 5 signal, all of this goes out the window, right? You have to have this connection, to be able to say with a straight face that DFT are samples of the DTFT, you must have applied an n-point DFT where n is at least as much as the duration of your signal, okay? With that in mind, let's be more careful in repeating the things that I said. So let's say x is length, trying to be consistent with my notes, length L. And h is length P. What is the duration of their convolution? I asked you this question at the beginning. You said L plus P minus 1, correct? Okay. So then to take samples of this at 2 pi by n times k and say that, oh yeah, this is equal to y of k, the DFT coefficient, n must be at least if I choose my n to be at least L plus P minus 1 or perhaps more, then yes, those samples that I'm taking are the DFT coefficients. If I do anything less than that, no. Okay? So I have to also do these samples here. 2 pi by n k and 2 pi by n and k. So then you get hk xk, right? Again, I had to choose a capital N that's at least as big as L plus P minus 1. Therefore, it's automatically bigger than L and P, okay? So I actually have to pad a bunch of zeros in H and N, I'm sorry, in X to be able to do this, okay? Suppose I'm doing the convolution I asked you to do at the beginning, right? It was the convolution of alpha 0, alpha 1, alpha 2, right? With beta 0, beta 1, right? What I asked you at the very beginning, right? So how would I do this using, not really doing convolution, but using these FFT algorithms, DFT, right? So I know the answer has length 4. So I should do a length 4 DFT or more. 4 is good enough, so we can go with more, okay? So what do? I say, if this was my H and this was my K, I go to Python or MATLAB. I'm used to MATLAB. I'm old school, okay? So I go to MATLAB, say, capital H is FFT of alpha 0, alpha 1, alpha 2. Am I done? No, it has to be length 4 or more, right? If I decide on 4, I have to put a 0. How is it going to know length 4, right? I need to give it a sequence of length 4 so it knows it's length 4, right? So that means I have to plant a 0 there, right? And then I hit return, I get 4 numbers, presumably complex. And then I say X, capital X, FFT of beta 0, beta 1, 0, 0. There comes another number, okay? And then I say define Y as H times K, and it probably gives me an error because it says these are 2 vectors, you can't multiply them. Somehow you have to do a point-by-point, element-wise multiplication. I think in MATLAB you put a dot before that or something like that. How is it in Python? Oh, okay. Then do it in NumPy. No complaints. Okay. Oh, awesome. I like that. Maybe I should switch. H times K, right? And then how do I find the convolution? I say IFFT, inverse Fourier transform of Y. It will give me a length 4 sequence. That's the result of the convolution. Beautiful. It's 4 lines and so fast. no pain, no drag, no flip. Awesome. Okay, so okay, so when they taught you FFT, they probably did powers of 2 because FFT is easier to present that way. And 4 would do it, right? To a power of 2. If it's 5, then, I mean, if for other numbers there, you know, Python or whatever you're using, it will figure out some nice decomposition, the best one available. Okay? Is that fair to say? I don't know. I haven't done this in a long time, so. All I know is, okay, like you, or like a student taking 123 back in the day, I was introduced to FFT. When you're doing an 8-point DFT, you see these diagrams that show you why it's so fast and straightforward. They never tell you how it's done for 17, but all I know is if I do a 17-point FFT in MATLAB, it just works just fine. So it's doing something. I don't know what it is. I've seen the compositions of things, but I don't remember now. Okay, so take 123 if you're interested in doing more FFT, or 170 if you're interested in the algorithmic side of that. Should we go back to the polynomials? Okay, so I just want to draw an analogy here between what we are doing, signals, convolutions, their DFTs, etc. And again, if you took 170, and don't worry if you didn't take 170, if you don't want to know anything about this connection, okay? So it's just a little exercise. It's food for thought, if nothing else, okay? So, all right, let polynomial Q of S, let's call it. I don't know what else to use. Alpha n minus 1, s to the n minus 1 to alpha 1s plus alpha 0. Okay? I just defined a degree n minus 1 polynomial. N minus 1 because I want to be consistent with the DFTs and all that I was doing, right? Okay? So how do I represent my polynomial? Like, how do I store this data? How do I store it in my computer, right? So there are two ways to do it, right? Two equivalent ways to represent. Ways to, or two data structures, if you will, to represent this. One, you can just remember the coefficients, right? You can say, you know, these are my coefficients from 0 to n minus 1, you know, therefore I know my polynomial. Okay? An equivalent way of doing it is to evaluate this polynomial at n points. Actually, let me change n. I don't like n. I'm going to call it L, okay, because we'll connect things at the end. Yeah. Okay, so no big deal. I'll just L minus 1 s power L minus 1, okay, to L minus 1, okay? So the other way of storing your polynomial, if you will, is to store samples of your polynomial. S sub k, k from 0 to L minus 1. As long as those samples S sub k are distinct from each other, you have enough information to reconstruct your polynomial. Okay? So S 0 to SL minus 1, distinct points. Okay, let's say this is a polynomial of complex numbers, just to be most general. Okay, so you have selected distinct points in the complex plane, and you represent your polynomial this way, or take real, doesn't matter. So how do I go? How do you agree? Do you agree with that these are equivalent representations? Can I recover one from the other? This side is easy, right? What do I do to go from that to that? Just evaluate your polynomial at those points, right? Just evaluate. Evaluate Q of S. How do I go back? Interpolate. So if you have L distinct points if you have evaluated your polynomial at L distinct points, and if your polynomial is degree L minus 1, you can recover. There's interpolation methods. You know, there's a one-to-one correspondence between these values, distinct values, and the coefficients. I think there's a name, is it called Lagrange interpolation? There are some formulas and such for that. The important thing, of course, you don't want to repeat your samples. You want distinct samples from each other, right? But if I have a fourth order polynomial, which is represented by 5 coefficients, I can just take 5 samples out of this polynomial for 5 different values of s, and that's enough to reconstruct the polynomial. So do you agree this is like taking, you know, this is like equivalent representation of the polynomial, the two? Okay. So essentially I'm going to, this is a little like x of n, right? And this is a little like x of k, because at the end of the day we have, you know, L numbers, right? They equivalently represent the same thing. Okay? So it's similar in a sense. In fact, this would be so let's make a note here. This would be exactly the DFT of our sequence of coefficients if I select my samples according to what rule? You're not saying it confidently. Oh, okay, roots of unity. E to the negative j and 2 pi over L times k times n, right? If I take this, substitute above, right? What I'm really doing is the definition of DFT, right? So DFT can essentially, if you want to look at it that way, if you don't want any connection to DTFT, Fourier series, if you don't want to know anything about Fourier, you can, and that's exactly what they do in 170. They want to introduce DFT without going into all of that. So they introduce it probably with this polynomial sense. Okay, so any distinct values sk would have been an equivalent representation of the polynomial. But if I select my points this way, I'm talking about the exact DFT, right? Okay, so you know that's a way of looking at, you know, polynomial coefficients as if they're a signal, and the DFT is like evaluations of the polynomial at distinct points, right? So that kind of gives you a little more sense about the DFT. But then let's see what it means to multiply the two polynomials. That's why I asked you at the beginning. I said multiply Q of S and R of S. Maybe I didn't call it R, I don't remember. But let's now define R of S to be another polynomial, beta, let's say degree P minus 1, beta 1S plus beta 0. All right? And I want to find Q of S times R of S. That is going to be a polynomial of length of degree L plus P minus 1, right? S plus something. And those coefficients will come from the convolution of the coefficients of the individual things, right? So that's why I asked you this at the very beginning. Let's go back. Yeah, well, that's why I asked you. So the convolution you found at the top must match the coefficients of the polynomials you find at the bottom. Okay? So these coefficients then would come from, these all would come from what? Oh, yeah. I just didn't write it because I'm lazy. S, you mean put this down? Be precise. What? Oh, yeah, you're totally right. Yes. Thank you. This is 2 you're saying, right? Of course, yeah, because that's degree L plus P minus 2. That means I need L plus P minus 1 coefficients for it, right? Because there's the 0th power. Okay, so basically alpha n convolution, the convolution of the sequences alpha n and beta n will give me these coefficients as you've seen in that little example. Okay? But that's, as you know, is a messy operation. It's a lot of work. It's a lot of computation. Instead, wouldn't it be easier if I just evaluated the product at enough many sample points? Right? So basically so if you're trying to multiply polynomials, it's a lot easier to work in this domain. You just multiply them, take samples, which means multiplying their samples, than doing the convolution of the coefficients, right? Just the way that we found in our previous page that doing convolution in the frequency domain is easier. In this polynomial analogy, it's much easier to multiply polynomials in terms of samples than